Okay, so I'd like to introduce Martha. She's going to talk today about the cohomology of nilpotent Hessenberg varieties and the dot action representation.
Great. Well, thanks for the invitation. Let's see. It's a little bit awkward, but I hope that folks can sort of hear me well enough, and feel free to stop me with questions. So yeah, and everyone can actually see my screen okay, the slide about my sort of title slide. That's okay.
Looks good.
And if I like use my pointer, can you see that?
Yeah.
Okay, wonderful. Okay, really great. Okay. So yeah, I'm going to talk today about cohomology of nilpotent Hessenberg varieties and the dot action representation. And I'm Martha Precup. I visited before, so I probably am somewhat familiar to some of the folks in the audience. But I'm at WashU, and then this is joint work. Part of what I talk about today is in a paper that I've written with Eric Sommers. And I can hint at some of the other things that we have that are work in progress. Okay, so I want to tell you a little bit about Hessenberg varieties. These things live in the flag variety. So I think that I will start with a slide about the flag variety. So for today, I want to be thinking about subvarieties of the flag variety. And I'm going to give you like a little bit of the sort of, there's like a quote unquote type A story, and then the sort of more general type. So a full flag in n-dimensional vector space is just a sequence of nested subspaces. And I guess I could have been a little more careful and made these properly nested subspaces. So each time I'm actually increasing by 1 in dimension. So I have exactly n of these subspaces, and I start with a 0-dimensional and then contain it in a 1-dimensional, 2-dimensional, until I recover my entire vector space. And the flag variety of GLN, although I guess maybe for my talk today, I'm really going to be doing the sort of the SLN case is the set of all full flags in CN. And we have an identification between, gosh, I see I wrote G everywhere on this slide. Okay, we'll just change that to S. We'll have an identification between the set collection of full flags and the homogeneous space SLNC mod B, where B is all the upper triangular matrices in in SLN, also known as a Borel subgroup. Where, you know, you could take your favorite matrix over here, and, you know, you could think about the flag that you obtain where you decide to take, you know, VI, the ith subspace in your flag would be the span of the first I columns of G. Okay. So if you take the map from SLN to the flag variety that takes in a matrix and spits out a flag, so that that ith subspace is the span of the first I columns, you can check very quickly that you sort of, once you quotient by B, obtain this bijection between these two spaces. Okay. But in general for today, this is sort of the type A story, sort of a concrete way for us to think about flags, but I'm going to let G be an arbitrary semi-simple algebraic group over C, complex algebraic group. B is just going to be some fixed Borel subgroup. G mod B is going to be my flag variety. I'm going to take T and G to be a maximal torus, and then W is the vowel group of my G. And I think maybe W is the only thing in this slide that's not discussed in the type A case. So what do I get? Like, what would be the vowel group in the situation when I'm working with SLN in this sort of like type A situation? Then the vowel group, well, T, I could take to just be the diagonal matrices in SLN. Diagonal matrices of determinant 1, and if I ask what's the normalizer mod T, we can see that we can identify W in that case with the symmetric group on n letters. So that's one of our primary examples in today's talk of one of these file groups that arise. This is just the symmetric group. Like quote unquote, just the symmetric group, because there's a lot of meaningful information and a lot of interesting things that hold in that situation that we're trying to generalize. Okay. Any questions so far? Okay. Okay, so what are Hessenberg varieties? So I am going to start with what's called a Hessenberg space. So I'm going to take a B invariant subspace of my Lie algebra. So this is invariance with respect to the adjoint action. The group is acting on the Lie algebra, and I can think about the subgroup B as acting on the subspace. And I want to focus on those subspaces that are invariant under this B. And so let's just get a concrete idea. So here's one case that we could always pick. We could always take the Lie algebra of the Borel subgroup, and that would be a perfectly good Hessenberg space because it will, of course, be invariant under the adjoint action of the corresponding group. We could also have taken the Lie algebra of our maximal unipotent subgroup, right? So I could take in my type A example, I could take the subgroup that's upper triangular with all ones on the diagonal. And that has a Lie algebra that corresponds to strictly upper triangular matrices in the Lie algebra of little SL. And I have that, and that's a perfectly good Hessenberg space. And here's some other things that I can do, right? So here's just like an example for n equals 4. If I'm living in SL4C, I can take the subspace consisting of all matrices where I'm allowed to put any entry that I want where I see those stars, but all of these entries are forced to be 0. So subspaces where those particular entries are 0. And you'll notice I call this H perp, because in fact, this is the orthogonal complement of this particular H under the killing form in my Lie algebra. I could take this subspace of matrices where I've decided to let only these top 3 entries be non-zero, and then anywhere else I see a 0, I'm forcing entries to be 0. And you can sort of see, I hope that these things, especially in the sort of type A setting where I'm working over SLN, are very combinatorial in nature. So let's just point something out here. So if my Hessenberg space has certain entries prescribed to be non-zero because of the way of the adjoint action with B works, like here, I'm just talking about conjugation, right? The action by conjugation. And so if I take an arbitrary matrix and I conjugate it by an upper triangular matrix, well, what happens? Well, things that are non-zero in my original thing get pushed up and to the right. This is sort of the way the conjugation works with respect to an upper triangular matrix. And so you can see this play out in these examples, and you can kind of see it by drawing a path. So I indicate, there are certain things that have to be 0. And then once I know that some entry is non-zero, conjugating by something upper triangular gives me non-zero things anywhere above and to the right. I could fill in the rest with possibly non-zero entries. So your hands are tied. Once I know some entry is non-zero, above and to the right is also going to be non-zero. And so you can tell that these Hessenberg spaces in this type A setting are in bijection with paths, lattice paths, to go from one corner of my matrix to the other. And in particular, you can also record this data with a vector, say like 2, in this case, 2, 3, 4, 4. That's called a Hessenberg vector. And all I'm doing is just recording where I've decided to take a horizontal step in each column, right? So here, In the first column, I move to the right once I go down 2, and then in the second column, I take my horizontal step in the third spot, and then 4, 4. And then similarly, I could also record this as a vector 0, 0, 1, 2. Okay, so if I give you the data of a Hessenberg space, and I give you any old element of the Lie algebra, so these are the 2 pieces of input data that I need to define a Hessenberg variety, then my associated Hessenberg variety is just going to be all of those cosets in the flag variety. So that G inverse XG, and really maybe I ought to write here, you know, the adjoint action of G inverse on X. See, I'm getting too used to working with matrix groups, as landed back in H. Okay. And so that's the sort of coset way of writing down the definition. You might ask, well, what about the sort of type A realization? If I were thinking about flags as nested sequences of subspaces, I could have also written this as all of those full flags with the property that X maps the ith subspace into the H of ith subspace, where this little h here is this vector that's just recording what the Hessenberg space looks like as a matrix subspace. It's recording where my zeros start. Okay. So, all right, Hessenberg varieties, we have one of these varieties for every single Hessenberg space and every single element of Lie algebra. Of course, like if you hand me 2 elements of the Lie algebra that are conjugate under the adjoint action, in fact, it's very easy for me to show that those Hessenberg varieties are isomorphic. So it's sort of a collection of varieties that are parameterized by these Hessenberg spaces, but also parameterized by the data of conjugacy classes in my Lie algebra. So the structure can vary widely depending on what input data we start with. So there's 2 particular kinds of Hessenberg varieties that this talk will focus on. So one particular case, I'm going to call them nilpotent Hessenberg varieties, and that's just because I'm going to choose my element of the Lie algebra to be a nilpotent element. And I'm going to pick a Hessenberg space that's what's called an adnilpotent ideal. So I am going to focus on Hessenberg varieties, Hess xi, where, like I said, X is a nilpotent element of my Lie algebra. And I is a Hessenberg space, but I'm giving it a special name. It's called an adnilpotent ideal. And all that I mean by that is that I is actually contained in this sort of strictly upper triangular matrices. So that would be the sort of type A kind of setting. You would take the nil radical of your Lie algebra and you'd require that your Hessenberg space be contained in that nil radical. That's what we get for these adnilpotent ideals. And if you're sort of familiar with adnilpotent ideals, chances are you've also seen them come up. They really go hand in hand with studying the structure of the root system associated to your Lie algebra. So the collection of all adnilpotent ideals is in bijection with upper order ideal subsets of roots. And these things have been sort of studied and counted, and there are sort of nice Lie theoretic formulas for them. So it's sort of the like Lie theoretic generalization of that sort of type A combinatorics, where we were seeing like, okay, you have a sort of lattice path dictating your subspace that you're taking. Sort of these adnilpotent ideals are dictated by that kind of combinatorics, but an arbitrary Lie type. So we have a sort of, in type A, there's Catalan many of these things, and in general, there's sort of a vowel group Catalan number that tells us how many of these adnilpotent ideals there are. The other kind of Hessenberg variety I'm going to talk about is called a regular semisimple Hessenberg variety. And that means that I'm going to assume that the matrix I'm using to define my Hessenberg variety is in fact in the regular semisimple collection of my Lie algebra. So if I go back to my SLN setting, that means that I have a diagonal matrix with distinct eigenvalues. And in this particular setting, I must assume that the Hessenberg space I'm taking contains the Borel subalgebra. Otherwise, you can actually convince yourself pretty quickly that this Hessenberg variety would be empty, because as soon as I choose a regular semisimple element, in fact, I know that I can sort of conjugate it to be a particularly nice form, and that kind of particularly nice form is only going to be an element of a Hessenberg space if it contains the Borel. So what this sets up for us is like there's a natural bijection between these two collections in some way, at least at the level of the Hessenberg spaces, because if I have a Hessenberg space used to define my regular semisimple Hessenberg variety down here, I can take that and turn it into an ad nilpotent ideal by looking at its orthogonal complement under the killing form, just like in that example on the previous page. So we do get this bijection between Hessenberg spaces containing our Borel subalgebra and Hessenberg spaces contained in the nil radical of the Lie algebra under this sort of orthogonal complement operation. Of course, down here, I'm only taking one kind of matrix, a regular semisimple matrix, and up here, I'm allowing myself to vary these matrices over any nilpotent orbit I'd like in the Lie algebra. So for us, one of the motivating key facts of this talk, which is due to Tomasco, is that the Val group W acts on the cohomology of these regular semisimple Hessenberg varieties. So we get a representation on this cohomology, this graded representation, and we'll call this the dot action representation. So we get one of these representations for every single Hessenberg space that we pick. Any questions? Okay. So what is this representation and how do you compute it? I mean, really those two questions can be thought of as the motivation for this talk. And actually quite a lot is known in this SLN setting that I was already telling you about. So in the sort of type A situation, we have a lot of combinatorics at our disposal to study this representation. And in fact, there are two algebraic combinatorists who are working on this problem, and they took Tomasco's graded representation and they conjectured. So it was originally a conjecture, and then it was proven later by Brosnan and Chow, I think just a few years after the original conjecture appeared, that when we apply the Frobenius characteristic map, which is just a thing that takes in our SN symmetric group representation and spits out a symmetric function, because folks in algebraic combinatorics like to think about things in terms of symmetric function, that when you actually put in the data of this Hessenberg representation, this dot action representation, you get out a very famous symmetric function. But there's a grading, so technically it's a quasi-symmetric function, but the thing that you get out of the machine is the Stanley's chromatic quasi-symmetric function. And I sort of said on H. So in our type A situation, that data of that Hessenberg function is encoded by a lattice path or a Dick path. And so that combinatorial data can be used to define a graph, a finite graph on n vertices with certain number of edges. And there comes in the chromatic part of Stanley's chromatic quasi-symmetric function. So it's a very famous symmetric function that you can define using the data of these finite graphs. So that's all sort of good, but the question is, well, like, do we actually know how to compute it? And the great news is that yes, we do. So folks in combinatorics have known how to express Stanley's chromatic symmetric function in terms of Schur functions for a long time. And the Schur symmetric functions on sort of this side of the story correspond to irreducible representations of the symmetric group on the other side. So we actually know how to break down the dot action representation into irreducibles. It's simply because folks in combinatorics have studied this decomposition on the symmetric function side. And there's a very concrete combinatorial formula for what the polynomial appearing as the coefficient is. So if I'm representing the sort of, so this is my representation for the sort of character of this dot action representation. So I'm using V sub lambda to denote the irreducible representation of the symmetric group indexed by partition lambda. I expect this Q lambda H polynomial to be an element, a polynomial with positive or non-negative integer coefficients. And in fact, like folks in combinatorics not only like can tell you vaguely, oh yes, of course, well, we know from representation theory, oh yes, of course, like we can write this as a sum of irreducibles. So we expect these to be non-negative integer coefficients, but they can tell you precisely what integer it's going to count something. There's a very concrete formula there, which is really beautiful. On the other hand, there are other questions about this representation, which translate to questions about these chromatic quasi-symmetric functions that are still wide open. And this has also motivated a lot of research in combinatorics, especially algebraic combinatorics and symmetric functions over the past like 10 years. So there's an open conjecture due to Stanley and Stembridge that this, well, I'm phrasing it in terms of the representation theory on the Hessenberg side, but the way to phrase it there is that the dot action representation is actually a permutation representation. So what that means is that not only do we have a representation of the symmetric group, but it can be written as a sum of representations that are induced trivial representations from reflection subgroups in a very nice way. Another really nice fact about these representations that's sort of obtained from the combinatoric side of the picture is that this dot action representation and its character is uniquely determined by linear relations that are known as the modular law. So folks in combinatorics observed this a long time ago.
Is there a question?
Yeah, so when you talk about permutation representations, are they induced in one subsystem?
I am so sorry, I can't hear. Can somebody type the question into the chat or something?
Are the permutation representations induced from young subgroups?
Yes, yeah, that's what sorry, if I heard correctly, the question is, do I mean permutation representation? And yeah, in this sort of like type A in the symmetric group, every reflection group is conjugate to a young subgroup, I think is the sort of classical result. So if you're going to induce the trivial representation from a reflection subgroup, then you're inducing the trivial representation from a young subgroup. These two things are equivalent.
Thank you.
Yeah, no problem. Cool. So, okay, yeah, so my last little point there was, you know, there's also these sort of linear relations called the modular law, which uniquely determine these representations. So again, this is a type A phenomenon. And let me just go ahead and give you just like a really tiny taste of what this modular law is. So remember, I'm just reminding you of the notation on the previous slide. You take the character of your dot action representation, which we're going to express in terms of the basis of irreducibles. There's some polynomial coefficient here. And so the modular law takes a triple of Hessenberg functions, or really, I think the whole time I've been reviewing, I've been calling these Hessenberg spaces, right? The Hessenberg function was just that, the vector recording where we take our horizontal steps. And so the modular law from combinatorics, so folks in combinatorics view it as a law on Dicke paths, right? We're viewing it on Hessenberg spaces, but equivalently, you have these lattice paths that are determined by where the zeros are. So in our situation, we have these various paths. And the modular law, I'm being a little hand wavy here, and I'm not giving you a very rigorous definition, but I'm giving you a definition by example, says that if you're in a situation and you can get a triple 1, 2, 3 of these functions, and you can go from one function to the other by just toggling a corner, right? So here, this middle guy, there's a corner here that if we just flip the corner, remove the corner, I still have a well-defined Dicke path, a well-defined Hessenberg space. And then similarly, I can take this empty thing, well, this was a corner, and if I flip this corner, I get this other one over here. So anytime you have sort of a triple where you can go between these things by flipping corners, and there's actually 1 or 2 other conditions that need to be met, which I'm going to get to in a little bit later. But definition by example, so in this kind of situation, then you get the following relation among the polynomials that determine the representation, right? So in that situation, the representation for the middle guy, or 1 plus t times that representation, you have to shift things, is equal to the shift of the smallest one plus the largest one. So that sort of intuitively, you have this triple, and this rule tells you how to relate the representation appearing in the middle to the representations corresponding to the Hessenberg spaces appearing on either end. So this is a very nice law. And it gives you a lot of leverage in quickly computing these things, right? Because you might want to test Stanley and Stembridge's conjecture for very high n. And one way to do it is to ask your computer to recursively do it using this law. So we had some motivating questions. So Eric and I, when we started doing this project, we wanted to think about, well, okay, what about this dot action representation? Tomasko's representation was for arbitrary vowel groups, not just symmetric groups. So what can we say in other Lie types? Can we show that the graded characters in the other Lie types satisfy this modular law? How do we make sense of this modular law for arbitrary vowel groups, for arbitrary Lie algebras? Can we actually, like in type A, I said the combinatorics have given us simple formulas for these coefficient polynomials. And I'd like to know, can I find some kind of formula? What is this representation? And then, of course, Stanley and Stembridge's open conjecture about, writing the representation as a sum of permutation representations. Is there a generalization of that conjecture for all Lie types? And maybe just to give you a taste of where we're headed, what we're going to see is that there is a version of this modular law for arbitrary Lie types, which is good. As of yet, I do not know of a simple formula. So determining what this dot action representation is as a sum of irreducible vowel group representations is still quite difficult. We don't have a great answer. And then generalization of the Stanley-Stembridge conjecture. So I want to say that I have confirmed with Eric, we have been working on this problem. We've been trying to think about what's the right generalization. All of this, there's several different things you could try to generalize, right? Like in type A, the question is, well, I want representations that are induced trivials from reflection subgroups. So I could try the comparable thing in other Lie types. I can say, well, let's try and write this representation in terms of those that are induced from reflection subgroups. Do I get some positive decomposition that way? And the answer is no. So there are some very easy generalizations that we have tried, and we do not have a positive answer. There's not the generalization in that way. but we're trying different collections of representations that generalize those permutation representations in type A to find some sort of generalization for other vowel groups. Okay, so one of the key things that we did when we were thinking about this problem is, you know, you have to answer the question, like, how do you even go about computing this thing? It's not easy at all. And in fact, like, trying to make the right identifications and trying to even in small rank cases do examples and determine what representation of the vowel group you get is non-trivial. So sort of the first part of what I want to talk about is how we went about this computation, or how we went about getting our hands on examples. So what do we do? Well, we focused on this particular morphism. So we looked at this map from G cross upper B of H, this sort of mixed space down to G, which sends the pair G and X to GX, G inverse. And it's a pretty easy fact that if you looked at the fibers of this map, mu H inverse of X, if you fix an element of the Lie algebra down here and look at the fiber over it, you get a variety that's isomorphic to a Hessenberg variety. And this construction might look very familiar because if you're very familiar with Springer theory and the Springer resolution, this is exactly a generalization of the Springer resolution. So if you looked at the special case where your Hessenberg space was exactly the nil radical of the Lie algebra, and you use that to do this construction, you get precisely the Springer resolution. And this is really helpful to us because this gives us a way of keeping track of irreducible vowel group representation. So we can leverage some Springer theory here. So the theorem due to Springer is, of course, that our vowel group actually acts on the cohomology of these fibers, which they are Hessenberg varieties, but you know, these predate Hessenberg varieties in the literature known as Springer fibers. Every irreducible representation of a vowel group appears on the top dimensional piece of the cohomology, corresponding to a unique nilpotent orbit. There's also an action of the component group here, which again, when we're working in not type A, we have to take into account this component group action because in not type A, it can be non-trivial. But the theorem and the Springer correspondence as it is says that every irreducible vowel group representation corresponds to a unique pair of nilpotent orbit, comma, representation of that component group. And I'm gonna just take the sort of, if you give me your favorite irreducible representation of the vowel group, I'm gonna pick the nilpotent orbit so that that irreducible representation occurs in this top degree component. And this action of the component group commutes with the action of the vowel group. So it will also occur in a particular, so right, this piece on which this irreducible W representation occurs will be uniquely also pull out one of these characters chi of our component group. And so classically, like this is a sort of the big picture here. This Springer correspondence is a nice way to keep track of things. And then folks in the audience might recognize that, okay, like the ordered pair of nilpotent orbit and representation of the component group also keeps track of the data of simple perverse sheaves on the nilpotent comb. So that in fact is an injection, right? Every simple perverse sheaf corresponds to some pair of data like this, but not every single one of those pairs might show up in the Springer correspondence. So how can we leverage this? So here's what this is what we do. We have to make use of some theorems that were thankfully in the literature due to Brosnan and Chow and Balbanu-Crooks. So in fact, okay, let's go back to our Hessenberg setting. We have this morphism G cross upper B of H to G. And we can restrict it over the regular semisimple locus. And This particular restriction gives us a monodromy action. So we can look at the fundamental group of the regular semi-simple elements in the Lie algebra with respect to some base point. That's going to act on the cohomology of the fibers, so we get an action of that fundamental group on the cohomology of regular semi-simple Hessenberg varieties. And if you sort of tease out the definitions and you tease out what's going on here, you in fact also see that this fundamental group surjects onto the vowel group. And so you can check now that this monodromy action in fact factors through the vowel group. And this is another way to think about the dot action representation. So the action of the dot action representation on this homology of these regular semi-simple Hessenberg varieties, in fact, coincides with the monodromy representation. So this was something that was established in type A by Brosnan and Chow. They actually established this as part of their proof of this conjecture that related the dot action representation to chromatic quasi-symmetric functions. And then later, Balabanu Crooks came and actually just filled in the details to have this hold for all E types. So yes, so we can view this dot action representation via the monodromy action, and that means that we can apply some formalism from the theory of perverse sheaves. That lets us use the Springer correspondence that we had on the previous slide. So what we do is we have on one side of this picture, we have, you know, the G cross upper B of H, mu H floats down to G. And let me stress that on this side of the picture, I want to think always about these are the Hessenberg spaces that contain my Borel subalgebra. So this is where the monodromy action is living over here, because this is where I actually get something non-trivial when I restrict over the regular semi-simple locus. But the Fourier transform for perverse sheaves says I have an equivalence of categories to work with here. I can also, if I want to push forward the trivial sheaf and I want to think about how it decomposes, I could also apply the Fourier transform and work over here with respect to the orthogonal complement under the Killing form. So here, if I think about my orthogonal complement, now I'm thinking about a Hessenberg space that's strictly contained in the nil radical of the Lie algebra. So understanding how the push forward of the trivial sheaf decomposes on the left-hand side, well, by applying the Fourier transform is equivalent to understanding how the push forward of the trivial local system, the trivial perverse sheaf decomposes on the right-hand side. And the really nice thing about the right-hand side is that H perp is now very small comparatively, right? I'm contained in this nil radical of the Lie algebra. That means that the image of this morphism only hits nilpotent elements of my Lie algebra. And now I'm talking about perverse sheaves on the nilpotent comb. And I can think about using the Springer correspondence here to determine the right-hand side of this story. So the long story short is that instead of actually thinking about the left-hand side, we actually want to think about the push forward for H perp. So now we can think about these nilpotent Hessenberg varieties for add nilpotent ideals. And we want to push forward that trivial sheaf and understand how do these decompose. And the theorem that Eric and I were able to prove is that the simple perverse sheaves that do show up in this decomposition all arise in the Springer correspondence. They're all things that actually show up in the bijection under the Springer correspondence. So roughly our proof idea was to adapt a decomposition. So you want to think about the cohomology of these Hessenberg varieties, these add nilpotent Hessenberg varieties. And we wanted to think about the action of the component group because that's an essential ingredient that you have in all A types that you do not have to worry about in type A. And we adapted So classically, there's a paper of DiConcini, Lustig, and Perchese that sort of studies this question for Springer fibers. So we adapted a decomposition they gave for the cohomology in that paper to the setting of these more general Hessenberg varieties, where you still have a nilpotent element of the Lie algebra, but instead of taking, well, for the Springer fiber, you're taking the full nil radical as your Hessenberg space. We're replacing it with an arbitrary nilpotent ideal in that nil radical. So this was the idea of the proof, and it allowed us to show that the things that show up in this push forward are things that actually show up in the Springer correspondence. And that's very helpful. It tells us, well, maybe just to quick go back to this slide right down here, this is kind of the essential correspondence here. That tells us that everything that shows up over here, we know exactly what it corresponds to over there. And because it's something that showed up in the Springer correspondence, the thing that shows up over here is telling us which irreducible vowel group representations come in the monodromy representation, show up in the monodromy representation, which ones are actually going to contribute to that dot action representation decomposition. So one nice corollary, just to point out of this, is that when you compute the Poincare polynomials of these nilpotent Hessenberg varieties, there's a very concrete formula here where you have, these are sort of the coefficients we had before from the dot action representation. And now you just have a translation that you're working with, because you're working with the Springer correspondence. There's sort of a translation polynomial that also appears here called like a green polynomial. And there's a T inverse, just to point out that this T inverse, there's some dimension shifts that show up, because when we apply the Fourier transform, there's some shifts that we have to make to sort of force things to be perverse in the right way. So let me just say that when you're back in the type A case, this formula, what it says is that you can write the Poincare polynomial of a nilpotent Hessenberg variety as a sum of polynomials where these guys are the polynomials that showed up in chromatic quasi-symmetric function language. And these coefficients are a very famous collection of polynomials called modified Koska-Fox polynomials. So combinatorialists have formulas for both of these things. So it's kind of nice. We can actually recover the full data of the Poincare polynomials of these nilpotent Hessenberg varieties, which is not trivial to do, using known combinatorial formulas for these two families of things. Of course, we were also motivated by trying to do the opposite. We're trying to recover the data of what is the dot action representation and other Lie types from the Poincare polynomials. So we would also like to independently compute those Poincare polynomials and then use that and the data of what the green polynomials are to recover what is this dot action representation. And so I will say that there's not sort of closed formulas for these things, but there are methods for computing these Poincare polynomials whenever G is classical. So Lucas Frossa has a paper that addresses the classical case. As myself and a student of mine thought about the sort of specific combinatorics of type A. But then you can also think about some of the other exceptional cases. So there's also a paper that addresses G2, F4, and E6. But there are still cases where we're not quite sure sort of how to go about computing these Poincare polynomials. So I'm running low on time, so let me sort of get near the end of my story. Remember, we had that modular law, and I said, well, okay, we'd also like to see some version of this law that holds in all Lie types. And one thing, if you start staring at this modular law triple, I said, okay, we need to be able to move between these Hessenberg functions by toggling corners, right? I see something that was a corner, and I can move to something else by just deleting that corner and getting rid of it. Another important thing that you pick up as you start to look at these examples is that there's a lot of symmetry here in terms of permuting these Hessenberg spaces by elements of the vowel group. So in particular, if you stare at these two end pieces, something you'll see and notice pretty quickly, let's see, is that this is invariant under the simple reflection that swaps the first two rows and the first two columns. And so is this H2 guy. And the guy in the middle is decidedly not, right? I can just sort of see for this H naught, the way that it's defined, swapping the first two columns or swapping the first two rows isn't going to do anything. Similarly for the very other end case. But the guy in the middle, swapping the first two rows and the first two columns is going to mess with precisely this entry that was sort of the corner I had to toggle to move back and forth between these things. So there is a nice generalization of these triples of Hessenberg spaces. So we call them a modular triple, but actually these already appear. It's sort of interesting, like this idea actually shows up already in that paper of decontinuous Lustig and Perchesi I referenced earlier. So they were studying Springer fibers. And then Eric Sommers and one of his graduate students, Molly Fenn, also studied these sort of triple of things. And so there was already sort of a definition out there in the literature that turned out to generalize this type A setting. So the definition says, well, sort of like in type A, we only ever want to increase the dimension by 1. So I'm going to require that H1 over mod H naught have dimension 1. So I'm only ever allowed to sort of, this idea of toggling a corner is going to turn into add 1 root space to an existing Hessenberg space. And then similarly, H2 over H1 also only increases the dimension by 1. And then we also will require that there's some minimal parabolic that fixes the smallest Hessenberg space, fixes the largest Hessenberg space, and in fact that the orbit through the middle Hessenberg space is equal to the larger H2. So once you establish this notation, you can see it's a lemma to prove, or it's a proposition we prove in our paper, that this definition does generalize this sort of like algebraic combinatorics definition that uses Dick paths. And in fact, you can prove that for any nilpotent matrix, you still have this nice relation between the cohomologies of your Hessenberg varieties. So I'm going to phrase this using the nilpotent Hessenberg varieties, right? There's going to be a translation of the cohomology of the middle that's equal to the sum of the Hessenberg varieties on either side, with a specific translation T there to just bump things up to the right degree. So this theorem was actually already in decontinuous Lustig and Perchesi for a very special case. They didn't prove it for arbitrary nilpotent matrices. They proved it for nilpotent matrices with the property that the nilpotent orbit was actually dense in the nilpotent ideal. Okay. And so Eric and I were able to tweak their proof, and you needed to do a little bit of legwork to actually show that in fact it works for arbitrary nilpotent matrices as well. So the corollary here is that this modular law in fact does hold in all Lie types, which is very, very nice for computing. So actually, let me go ahead and sort of like give a quick example before I end here. So you can say, okay, well, like this is good. We sort of have some idea of how to compute these representations. We have the modular law, which will help us compute these representations. And I think one takeaway is now things get more nuanced, because what happens is that in type A, the modular law determines everything you want to know about the representation, right? That is in fact like a theorem that some algebraic combinatorics proved like 2 or 3 years ago, right, that this modular law actually really dictates everything about these representations. Unfortunately, that's not true for all Lie types. So although we still satisfy the modular law, you need more information to uniquely determine the dot action representations. And it has to do with the fact that you can get these triples. So this is actually one of these modular triples. So here's an example. This is just add nilpotent ideals for B2. So these guys are telling me what my Hessenberg spaces are. And if you ask yourself, like, okay, what's this modular triple? How can I relate these using the modular triples? There's in fact only one modular triple that you can use. And then this guy, the problem is he's not in any modular triples. So if you're going to determine the dot action representation using only this modular law, you have to know what this ideal will give you sort of independently of all the rest of them. And that kind of thing just doesn't happen in type A. You're going to see that there's always a lot of ways to move between these ideals, and you don't seem to get these like isolated cases as often. So yeah, thanks for your attention. I think I'm going to stop there.
Can you go back to sort of the beginning of the talk?
So it's very muffled, but I think I heard somebody ask me to go back to the beginning. So I will try and do that. Is that right?
Yes.
Okay, great. How far into the beginning are we talking here?
Go on. No, keep going. Wait, no. Go.
Oh, that's the very beginning.
Right. A little bit more. Let's see. One more slide, maybe. Let's see, one more. Right here. So I'm looking at the Stanley-Stamberg conjecture.
Yeah.
Now, let's say you're in type B.
Yeah.
So, do you have any ideas whether this will actually be sort of like a direct sum of certain types of representations in that case?
So, okay, let's say you're in type B. So we have some ideas. So here's, like I said, I think I said this in passing, but maybe I'll say it again. One generalization you could hope for is you could say, all right, the type A permutation representations, one way to think about them is you're inducing a trivial character from a Young subgroup or from a reflection subgroup of type A. So you can say, well, okay, let's look at induced reflection subgroups. You induce a trivial in type B, and let's try and write this as a non-negative linear combination of those. We can find examples in rank 3 already where that fails. So you can find B3 examples where that doesn't work. However, okay, maybe going back to this idea of the modular law, using the modular law, you can sort of reduce to, if I cannot, you can sort of find a sub collection, maybe I will say, of representations that are dot action representations that they seem to suffice for writing everything as a non-negative linear combination of them. But there's too many of, there's not like they're not a basis for representations of type B, if that makes sense.
So the way I think about permutation representations, they sort of sit inside like the tensor space. If you take a natural representation for like GLN and you tensor, let's say D times, it's going to be a representation for the symmetric group. And let's say N is big enough. And so the permutation representations basically sit inside of that. And then you can actually do this in type B.
Okay.
Okay. And so you can actually have the Weil group for type B act on the tensor space.
Okay.
And so my question is, can you use the summand of those tensors of that tensor space to maybe give you a set of modules for which you can realize this Stanley.
Oh, that's really, and so, I guess that I'm not quite sure, because what do those summands look like? Do you have a good,
Yeah, so we actually have a type B Cherval duality.
okay,
So, Cherval duality is something that you sort of mentioned in the Shareshian Wachs conjecture. And
Yes.
Yeah, okay. So we have a type B version of that now.
Okay.
With the tensor space. I can send you the paper and everything.
That would be great. So I will say that I've thought about several different generalizations in type B of what permutation representation can mean. And so I just am not sure if I've already thought about that collection of that you can see as summons of the tensor representation or not. That would be really interesting. And if I haven't, then I would be very excited to think about.
Okay,
If that
I'll send you the paper.
could,
Okay,
that would be really wonderful. Thank you. Yeah.
You want to come up here now? Here's another question. Okay. Sorry.
My question is that is there a version of like partial Hessenberg variety? I mean, like spaces that are figured by the parabolic subgroup.
Yeah, so absolutely. Yes, there is. So you can certainly say, let me go back to just that definition. So here's the definition of a Hessenberg variety, right? And what is important is that the Hessenberg space is B invariant under the Borel. So you can easily define a G mod P version of this thing.
Right, yeah.
And you're going to require that your subspace be P invariant.
Yes.
And I think that you can sort of, well, so the thing I want to say about those varieties geometrically is very quickly you'll realize that you can recognize each of the sort of G mod P Hessenberg varieties as sort of like an image under the projection of G mod B to G mod P of a Hessenberg variety living up in G mod B.
Yeah.
And like that projection map has all the nice properties you could possibly want, right? So in fact, like studying the geometry of the varieties in G mod P is gonna come, like, if you understand what they're doing in G mod B, then it will tell you what's happening in G mod P in a really nice way. On the other hand, like you can definitely ask a lot of these same questions, and there's still a dot action representation in the G mod P case. Yes. And like it might look slightly differently, but you can sort of go between them by sort of tensoring with the right number of trivials and the right degree. If that helps to answer your question. So yes, absolutely, you could think about a G mod P version of Hessenberg variety. I think the reason this isn't all over the literature already is that they tend to be easier than the G mod B. So folks focus on the G mod B version first. And I have yet to see like a G mod P paper that's vastly different results than just thinking about these things in G mod B.
When you say that the same under the projection is like the conjecture, so you have a map in G mod B, G mod B. So like the Hessenberg analog in G mod P is or in G mod B is the inverse image of the one in G mod P. Is that exactly the relation?
Sorry, that was a little garbled, but I think that the answer is yes. Like that if you were to think about the natural map from the natural projection map from G mod B to G mod P, well, there's a couple, you can just say, well, like take a G mod P Hessenberg variety and pull it back, and what is it? And it's a G mod B Hessenberg variety.
Okay, yeah, that's what I heard.
And sort of, so that means that if you understood the G mod B thing well enough, you would be in a pretty good position and you'd know exactly what's going on in G mod P also.
Right, but you might hope that there might be some like, if like Grassmannians is sort of simpler than the flag varieties, so you might hope that you could even, that those might be simpler in some way, even though you principally could get the information by pulling up the G-Mod-P.
No, I don't disagree. Yeah, I agree with that statement. I think that it depends on the question you're trying to ask. I think my point is that the questions about these dot action representations specifically, because of that map, the translation between those representations is pretty well understood, and that's not hard. So in the context of maybe like this talk, going down to G-mod-P it amounts to taking your representation, and it's like, it'll turn out you can sort of convince yourself that, you know, the coefficient polynomials that dictate which irreducibles appear are all divisible by like the Poincare polynomial for the parabolic that you are trying to go to G-mod-P of, right? So the representation itself doesn't change dramatically. It could be maybe that like there are some geometric questions that are better asked in G-mod-P. And I think one of the other things that sort of shows up here is that there's not being B invariant, these subspaces being B invariant is very restrictive. And if you're going to make it P invariant, let's say P was a maximal, or yeah, one of these maximal parabolics where you're taking like in type A, like a GLP cross a GLQ. And you ask like, okay, what subspaces of your Lie algebra are actually invariant under a maximal parabolic? Very quickly, you'll realize like not much that's interesting besides the whole Lie algebra or just the Borel. Like there are a few things that fall into this category, but they also have already appeared in the literature under other guises, like Spaltenstein varieties and what's some other ones? Steinberg varieties. You know, if you search literature on Springer fibers, you'll find these sort of G-mod-P versions of Springer fibers. And it turns out that, yeah, those things, what am I trying to say? Those things are closely connected to Springer fibers. And in the literature, you can figure out like, okay, understanding the Springer fiber really dictates what these G-mod-P Springer fiber things are doing. And so sort of the same thing might happen for Hessenberg varieties. I haven't teased out that whole story, and I don't know that there could be some geometric questions that are interesting at G-mod-P level that are not answerable at the G-mod-B level. So that would be very interesting. I don't know.
Can you change the algebra G to some other representation of the group P?
Oh boy, yeah, you definitely can. And that's truly the wild, wild west. You can change the Lie algebra to some other representation. You can change your Hessenberg space to any subspace that's invariant under the Borel subgroup. And you can try and figure out what kind of variety you have. And there are a few very special cases where I've seen this done. But like, if you want to really do this in a general way, I think it's very difficult. But yeah, that's a really good question. And yeah, you can even do that level of generalization.
If not, let's thank the speaker then.
Thanks, everybody.